back where we're at. So we're dealing with the ratios of these four elements. So that's a 1, as you can see there. Carbon is 4, hydrogen is 5, nitrogen is 2. Okay, so this brings us to our empirical formula. That's kind of what we've been going after this whole time. So we have C4, H5, N2, and O. And while this is the basic composition of caffeine, these numbers might be in their most prime form, so we might need to multiply it by a certain multiple depending on the molar mass. So what we need to do here is that since the problem gives us the molar mass of caffeine, we need to find the molar mass of what this empirical formula gave us, and then divide that by the molar mass of actual caffeine, and that should give us the multiple that we should apply to all these numbers. So if you go into your periodic table and find the molar mass of each of these four elements and multiply the molar mass of carbon by 4, hydrogen by 5, nitrogen by 2, and oxygen by nothing, add them all together, it brings us to, and you can pause the video and do this on your own, but 97.10 grams per mole. And the book told us that caffeine is actually 194 grams per mole. So when we do 194 divided by 97.10, we get about 2. And this number is not exact, but I'll show you the actual calculation. Alright, hopefully this time we won't run out of memory again. Alright, so back where we're at, we divided the molar mass of carbon by the molar mass of what the empirical formula gave us, which is about 2. So this is our multiple, and we apply this to the empirical formula, and that spits out our molecular formula, which is what we're going after this whole time. So the molecular formula is then C, 2 times 4 is 8, H, 2 times 5 is 10, and 4 O2. Alright. So this is our molecular formula. But we're not done yet, because the question still asks that we write the equation for its combustion. So putting it all together, we have our caffeine, C8H10, and 4O2, plus oxygen. And notice how I'm leaving a space in between these so we can add the coefficients. And this was a solid caffeine, gas of oxygen, and on the other side, CO2, gas, H2O, liquid, and N2 gas. Alright, so as we can tell, this equation is far from balanced. So using our intuition, we realize that we are going to need a lot more CO2 to get to this C. So starting from least complicated, so let's put 8 over here, for instance. So 8C, now we have 8C over here. That makes this 16O, and we don't have nearly as much O over here. We have 4O, not to consider this one, so that's 17 oxygen. So we realize that since this is an odd number on this side, we need to go to the next multiple. So let's go to 16. And for this side, now we need a 2 over here to compensate for that 16 carbon. So now the carbon is made up and on both sides. So now let's go to hydrogen. We have 10 hydrogen here. Sorry, we have 20 now, and we have 2 here. So put a 10 over there, that brings it to 20. Nitrogen, we have 8 over here, Put a 4 there, now we get 8. Alright, and now let's count how many oxygen we have on each side. On this side we have 4, 6 oxygen on this side. On this side we have 16 times 2 is 32, plus 10 is 42. We have 42 on this side. So, now we need to get the coefficient for this oxygen, which we find to be 19. So our final equation is then 2 over here, 19 here, 16, and 10, and a 4. And that's the reaction of caffeine, the combustion reaction of caffeine. And that brings us to our final answer. So thank you for watching, and leave any comments if you have any questions. Sorry my video jumped a couple times because my phone was running out of memory, so I'll make sure that there's a smooth transition in between those. Thanks for watching.